and welcome to that webinar. I'll be giving a high-level overview of the special issue that is basically driving the webinar, the underpinnings and the core ideas and the core parts of the. So first, what is the reason that we are talking about high-level specification and about high performance? If you look at today's hardware and software and the range of machines that are used is a quite wide range of machines. On the left side, you see in the science, engineering, and Department of Energy realm, machines may range from a desktop or workstation size to departmental or high-performance computing installations that are the size of a refrigerator or multiple refrigerators, all the way up to top supercomputers that may be the size of a soccer field. In the consumer and Department of Defense side of the world, the form factors are tighter, and you see very high-performance computing platforms in the form factor that fits into airplanes, helicopters, cars, but also in consumer devices like cell phones or even wearables like watches, and in particular in current cars that are to become self-driving. So this is quite a range of platforms, quite a range of form factors, and quite a range of potential computing power. And what software developers are faced with is to produce software that runs across this wide range of machines and utilizes the machines efficiently, because there would be no point in actually building these platforms if we were not able to utilize them. And so one observation is that standard coding techniques may be coming to their end when it comes to this wide range of machines. This was cross machines, but if we look into the complexity that a single machine, a single system nowadays might exhibit, let's take a system that we could buy off the shelf for about $1 million. A system like that might be a combination of large shared memory, maybe up to 6 shared memory, a number of field programmable gateway FPGA cards, large NVMe flash drives, about a couple of hundred terabytes, maybe up to a petabyte of spinning disks, then accelerators for graphics cards, GPUs like NVIDIA's DGX1 with 8 Tesla GPUs. So this system together would fit in something like an order of 7.5 kilowatts for less than $1 million. But now the question would be, how does programmers actually program a system like that? That would be the multi-kilowatt form factor. But if you look at a car has tens, maybe 70 processors in its network, and they all range from low power to high performance, just modern cars with entertainment and self-driving capabilities. It goes on in the scientific computing world, accelerators take over, and so the range of platforms that we have to address in modern scenarios is truly staggering. So historically, the idea would have been that we would use programs to basically to program the hardware. The idea that the right frameworks and programming languages are powerful enough to express the programmer intent, and then automatic systems compilers to map it and runtime systems to map it to the hardware. And as the hardware is more and more complicated, these relation systems have to become more intelligent and deal with a larger and larger range. And oftentimes, programmers are required to write algorithms and write their ideas in a way that does not exactly conform to the way they are thinking about their problem. So they have to optimize for the particular target platform, and that makes it harder for the runtime and compilation system to actually figure out what's going on. So a number of efforts have started looking in the idea of domain-specific languages and higher-level abstractions that lift basically from a program to the next higher level, which might be a domain-specific language program or a specification in mathematical language. And in that special issue, this is one of the aspects. Is it possible to lift the abstraction so that the compilation systems, runtime systems, know more about the problem and therefore can do things that are closer to optimal, while at the same time allowing users to express their algorithmic and domain knowledge in a better way without having to worry so much about what's going on. And so it's not a true left-right. Here, a lot of the systems on the left are trying to implement ideas right, but this is just giving you the idea of how can we lift from a programming language perspective to a more problem specification perspective. Then here is, when we look long-term at what is going on, is the way to go away from programming in a large number of programming languages for particular, say, big data accelerators, and go more to we express higher level what we actually want, and we are agnostic to the platform that it's going to run, and even if it's very futuristic platform. And so the special issue aims at trying to see where do we stand in this respect, what are the leading technologies and the leading projects across the world right now to address that. And of course, this is going from compilation and languages to program synthesis and beyond, and also talk about the top-end hardware. So in particular, if you look at the papers in the special issue, there is a section of papers that deal with modern versions of comparison and compilation and languages, and it's not a clear-cut partitioning, so some of the papers touch more than one of the domains that I'm talking about, but one paper talks about machine learning in compilers, another paper talks about domain-specific optimization for GPU and stencil, and we have Sadaf, who is an author on that paper. Sparse polyhedral framework going beyond the standard inspector executor is a topic. Also, how the high-level OpenMP approach helps us to hide more and more hardware and encapsulate more and more parallelism. The issue goes from compilation more towards program generation and program synthesis. There, the spiral system, where Jose Mura and I are co-authors on, talk about our approach there, but also on automating development in high-performance multi-grid solvers talks about program synthesis. And the British paper on navigating the landscape for real-time localization in robotics. And then, the special issue has an aspect on automatic performance tuning or auto-tuning and high-performance computing, and automatic performance tuning in numerical linear algebra from Dongara as an issue in the long and winding road towards efficient high-performance computing by Jalbi and David Cook and others. Then we have a paper from the Japanese side on Japanese auto-tuning in the context of large machines there. And auto-tuning in high-performance computing applications, more application-level auto-tuning. So you see how the special issue spec compilation, program generation, auto-tuning, and high-performance computing. This is the first area that you have to address in the new world with these complicated architectures. And what is going to happen in the webinar is that we take of co-authors and co-editors from the special issue to highlight special aspects that we are addressing here. And basically, Jose Mura will be talking about spiral. Sadai will be talking about his approach, and David Padua about the compilation side also. So these are panelists, and so I'll hand over to Jose Mura, and when we come back, we'll be ready to address your questions.